Okay, so we're here, 6.5, the conical tank. I really like these questions a lot. I think they're pretty cool, and they're fascinating to me. Maybe not so much to you guys, but it's okay. So here we go. The conical tank in the figure is filled to within 2 feet of the top with olive oil, weighing 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? So this is really important once you start getting into to large factories that have to transport liquids. It's actually a lot of infrastructure and logistics to move liquid around. Like I know one big question is like the countries in Africa that don't have access to clean water. A lot of people will say, well, why don't we just ship them clean water? And that's because liquid weighs a lot and it takes a lot of work to move liquid around. So here we just have some olive oil in this tank and we want to see how much work it's going to take to remove that olive oil. First thing I'm going to do is I'm going to try to copy this picture over to OneNote here. So here we go. You guys know my drawing at this point. I'm going to try to do it in 2 dimensions here. So we have our tank that looks something like this. That's not too bad. I'm pretty happy about that. Our tank looks like it goes up to 10, but the liquid itself is 2 feet from the top, so the liquid is only really here at 8. Another thing that it gives us here is it goes ahead and gives us the formula for the outside edge of the tank. This line that we have is y equals 2x if this were to keep going forever and ever. Okay, another thing that it gives us, which is pretty nice, is it does give us this location here. It says that this has an x value of 5. We could get that pretty easily just from the formula, though. All right, so what we are going to do, I'm getting away from the book here, is that we are going to try to figure out how much work it is to remove this whole thing. And there's kind of a process to it. There's not really a formula, but there is a process. The first thing that we're going to do is we're going to slice our olive oil into horizontal slices. So this particular horizontal slice, we're just going to say is located at a value y on the y-axis, just generic. And the first thing that we need to do is we need to figure out what the volume of that slice is. Now, because this is a conical tank, when I make a horizontal slice, we're going to end up with a really, really tiny little circle or cylinder here, if you want to think of it in 3 dimensions. So the volume of a cylinder is to find the area of the circle and then multiply that by the height. So the area of this, we just got to be a little bit clever with. So if you notice in the book, they didn't have it written like this formula, the y equals 2x. They actually wrote it the other way. X is equal to 1/2 y. The reason they wrote it that way is because if we are located at y, then the radius of my circle here is going to be the horizontal distance, which is the x distance. So if I'm at y, then this horizontal distance is actually 1/2 y. So that means that the area of the circle is going to be pi, that radius 1/2 y squared, right? So pi r squared to find the area. To change area to volume, we're just going to multiply by the height. But because this is just a little slice that has a tiny little height to it, my height is going to be dy. So this is going to be the volume of just this one slice. If I go up and down the y-axis, then this generically gives me the volume of every single slice. To simplify this down a little bit, we'll go ahead and square this. 1/2 squared is 1/4, and I'll bring that into the pi. So we'll write that as pi over 4, and then we have the y squared, dy. All right, from volume, the next thing that we want to find is we want to find the force that's being applied from that slice. To find the force, you're going to take the density and multiply that by the volume. Sometimes you also have to throw in the gravity constant if you're in the empirical metric system. Okay, let me go back over to the book's questions so we can get the density. The olive oil weighs 57 pounds per cubic foot. What that means is that if I multiply by the volume, which is the cubic feet, it's going to give me the pounds. So all we have to do to find this variable force here for that particular slice is to take that density, that 57. It's not writing here. What happened to my pen? Did my pen die on me? All right, hold on. Pause the video. All right, I'm back. The battery must have died on my pen here, so I had to go grab another one. All right, so what I was saying is that the variable force here is just taking that density, which is the 57, times what we already have for the volume. So that pi over 4 y squared dy. Okay, then from force, we want to get the work it takes to remove it. Oh, by the way, these little upside down triangle things are what we call deltas, right? So this is just the tiny amount of work to remove the one slice. Eventually, we're going to integrate over all of those. Okay, to find the work of that particular slice to remove it, we're going to take the force of that slice, or the weight of that slice, times the distance to get that slice to the top of the tank. If the top of the tank is located at 10 and my slice is located at y, then that distance is going to be 10 minus y. So we're going to take the weight, or the force here, 57 pi over 4 y squared dy, and we're going to multiply that by the distance to remove it, which is 10 minus y. Okay, we can simplify this down a little bit, so I'll distribute that 57 pi over 4 y squared into the parentheses, and we get this 570 pi over 4 y squared minus 57 pi over 4 y cubed, and all of that dy. This is the work to remove one slice. If I want to now find the total work to remove all of the slices, we're going to integrate over the work to remove one slice. So just copying this down. The limits of this integral are going to be where all of the slices are located. We have slices starting at 0, but it does not go all the way up to 10 because the olive oil doesn't go all the way up to 10. The olive oil only goes to 8. Okay, and now we just do this integral. So this y squared is going to go to y cubed, and then we're going to divide by that 3. I don't know if 570 divides by 3 evenly, but I'm about to find out. It sure does. It's 190. And then still have the pi over 4. This is now y cubed. Minus this divided by 4. So I'll write this as 57 pi over 16, y to the 4th. And then we're evaluating this between 0 and 8. So I'm not going to bother plugging the 8 into here. I'm just going to dot this one. I hope you guys can plug numbers into this stuff. I was going to go over to the book here and look at the final answer. So this 30,561 foot-pounds. So a lot, right? 30,561 foot-pounds just to remove olive oil out of a 10-foot tank. It's a lot of work to remove liquid. You can do some fun stuff now, like figure out the amount of work it takes to drink a milkshake. Just find the density of the milkshake, and then look at kind of the cup that it's in, and you can figure it out from there. There's all kinds of neat things that you can do at this point. But just to go through the process one more time, because this is some hard stuff and there's not a formula to it. Whenever you're removing liquid from a container, you have to cut it into horizontal slices. Find the volume of each slice. Usually they're going to be circles, but not always. They could be rectangles or some other shape. So here the volume of the slice was the area of the circle times the height, which we just labeled dy. To find the weight or the force of that slice, we take the density of the liquid times the volume. To find the work to remove that slice, we take the force or the weight, and then we multiply that by the distance to get it to the top of the tank. Then you just integrate over this, and you get your final answer.